Okay, we've reached the appointed time. It looks like we've reached the appointed capacity, so I'm going to go ahead and start talking. Welcome everyone, as you probably guessed. This is the functional thinking talk. My goal in this talk is to separate the functional paradigm from functional syntax. Most of the time when you start looking at functional programming, you're also being shown new languages and the syntax gets mixed up with the ideas. What I'm trying to do is concentrate on the ideas and not so much on the syntax. And so I'm trying to stay in very familiar kind of languages for the most part. And this talk is mostly focused around Java and kind of the Java ecosystem. But one of the arguments that I make in this talk is all languages are becoming functional languages, so it doesn't really matter which language you're in, you're going to see these same ideas pop up in lots of places, and in fact increasingly more places as time goes by. But I'm going to start with a metaphor, an essay, and a history lesson. Here's the metaphor. Let's say that you're a lumberjack and you're okay. You're the best lumberjack in the forest at cutting down trees with an axe. It's stunning how fast you can cut down trees with an axe. Then somebody shows up with one of these, but they don't show you how to use it. And so your first instinct as a lumberjack is to take the uncranked chainsaw and swing it against a tree and very quickly reach the conclusion that chainsaws are terrible ways to cut down trees. I'm going back to this axe. Because I've been using this axe for 10 years, feels really good in my hand, it feels familiar and safe and comfortable. This must be the best way to cut down trees. And then someone shows you how to start this thing, and you realize you can cut down way more trees with one of these. The point of this is that learning a new programming language is easy. We've all done this multiple times in our careers. It's really just about learning the syntax of how ideas are expressed in a new language. But learning to think in a new way is really, really hard. And that's what I'm really trying to tackle in this talk, is thinking about problems in a new way. And one of the things I'm going to try to illustrate in this talk is that functional is more a way of thinking than a particular tool set. That even in non-functional languages, you can still write more functional style code. Here's the essay. And it's a pretty old one, but it's quite entertaining. This is by Steve Yagi. He's a well-known blogger. Called Execution of the Kingdom of Nouns. He published this back in 2006. And it's about this mythical kingdom where nouns are first-class citizens and verbs are subjugated slaves. In fact, it's so bad in this kingdom until very recently, verbs were not allowed out on the streets late at night without a noun chaperone. And so much so that they invented a special kind of noun that has no nounness, that does nothing but chaperone verbs around late at night, because who knows what kind of trouble they might get into if allowed to wander the streets unimpeded. And of course, this kingdom that we're talking about here is really Java, and this insistence in Java and similar languages that everything has to be based on a class. And that's based on this idea that things in the real world have both properties and behaviors, and so that makes pretty good sense. But then it starts digressing into craziness like this, where you have to invent some syntax and basically wrapper things around other things just so you can pass behavior around. This is where it gets kind of silly that there are in fact verbs in the world and nouns, and there are combinations of nouns and verbs, and any language that tries to force you to ignore one of those things is probably deficient in some way. And so not surprisingly, this talk is very much about verbs and not so much about nouns. And we're trying to get away from asking objects to do things for us and just do them. I guess in this case, undo them. And here's the history lesson. You can go to the O'Reilly website and download this poster. It's a history of programming languages. And this is only the first couple of hundred programming languages. There are well more than 2,000 programming languages we've created since we started this in a relatively short amount of time ago. But I want to point you back to a particular era on this chart in the early 70s to early 80s, and point out the creation of this language, Simula 67. Does anybody know the significance of Simula 67? Some nice computer science trivia for you. Nobody?
Introduced object-oriented?
First object-oriented language, exactly. Simula 67, first object-oriented language. These are the guys who invented those concepts. And then in 1970, Smalltalk came along. And then in 1983, C++ came along. Now, there's a good argument to be had over pints about when did object-oriented programming become mainstream? Did Smalltalk make it do that, or did C++? It certainly wasn't mainstream before C++, because that's how a lot of developers first encountered those concepts. When you look back at 1967, the predominant paradigm then was to program using gotos. They didn't even have structured programming. That came along in '72 with Pascal and the C family of languages, and you would have thought that back then, as soon as they saw objects, it's like, oh yeah, we should be doing that. That's clearly better than this crazy stuff we're doing here. But it took almost 15 years for that realization to sink in. This happens all the time in the computer science world. We have a kind of mainstream of technology, and you have these offshoots. You have academic offshoots, and functional programming is very much started as a kind of an academic offshoot, a different way of thinking about problems. You have practical offshoots. The fourth generation languages in the late 90s is a great example of a practical offshoot. It kind of died away and went back to the kind of mainstream general purpose languages. But every once in a while, one of these offshoots comes back and rejoins the mainstream. And that's exactly when we see functional programming happening today. Every major language has functional programming bits in it, and there are good reasons why all these languages are adding these functional programming constructs. And we can take some really good advantage of those things. Now, one of the things I want to illustrate in this talk is the real difference between object-oriented programming and functional thinking. And Michael Feathers did a really good job of capturing this in a quote on Twitter, which is like a curse. So Michael Feathers says, that object orientation makes code understandable by encapsulating moving parts. Just think about what you know about the object-oriented languages you know, whether it's Java or C# or a language like that. There are a lot of mechanisms in a language to let you see some things but not change them, not see some things at all, and then see them and change them, and there's all sorts of wiring, and there's all sorts of scoping, visibility about, well, if you have this relationship, you can see it, but if you don't have this relationship, you can't. Those are all kind of moving parts around state. Functional programming makes code understandable by minimizing or eliminating moving parts. And we'll actually see examples of this over and over in the functional programming world. If you don't have to interact with this part, there's no way you can mess it up, and therefore you don't have to think about it anymore. The language or runtime handles those details for you. So I need some code if I'm going to be talking about programming styles, and I need a problem to solve. And so I'm going to take on the simple problem of number classification. This was something that was cooked up by an ancient Greek mathematician a few thousand years ago, and he made some interesting observations about numbers. And he identified what he calls a perfect number. So if you take the factors of a number, those are the pairs that when multiplied together equal the number. So for example, 6, 1 and 6 are factors, and 2 and 3 are factors because 2 times 3 equals 6. Well, this observation that he made was that there's some class of numbers that if you take the sum of the factors of the number and add them up, they equal the number itself. So the sum of the factors of a number minus the number equals the number, because the number itself is one of its factors. So another way of saying that is the sum of the factors of a number is equal to 2 times the number. So 6 is a good example of this. It's a perfect number because the factors are 1, 2, 3, and 6, which equals 12, which is twice 6. 28 is also a perfect number because if you take its factors and add it up, it's twice 28. So is 496 if you want to do the math to figure that out. It is in fact a perfect number. And this was the classification scheme this ancient Greek guy came up with, was that numbers where the sum of the factors equals twice the number are called perfect numbers. If the sum of the factors is greater than 2 times the number, it's called abundant. And if the sum of the factors is less than 2 times the number, it's called efficient. So any whole positive integer can go in one of these 3 buckets. So I'll write some code that handles this. I'm going to write it in several different ways. The first one I'm going to write is a purely imperative version based on Java pre-lambdas, pre-Java 8, which just came out a few days ago. And it's actually, if you want to get into the real details of why this example looks the way it does, this was an example I did for my book, The Productive Programmer, and this is in fact the sample chapter from that book, which is about test-driven development, and it built up this example. And so here is that example of finding perfect numbers. And I'll walk through this bit at a time. So I have 3 pieces of internal state here, and I'll show you why I have these 3 pieces of state. I have the list of factors, the number itself, and then the sum, because I'm going to cache the sums. The presumable use case for this code is that I needed to classify the same number over and over, and calculating the sum is kind of expensive. So for a given number, I'm only going to calculate the sum once and cache it, so that I don't have to do that work multiple times. That's what that guy's going to hold. I'll show you that code in a second. There's my constructor, which constructs all these guys, and it goes ahead and adds 1 and the number to factors because those are automatically factors of a number. This is the code that determines is a number a factor of another number or not. This is basically just using the mod operator that every language has. If factor goes into the number with 0 remainder, that means it is a factor, and that will return true. And so this calculates my factors, and this has a bit of an optimization in it based on an observation. Notice that I'm only looping up to the square root of the number here when I calculate factors, square root plus 1. That's because there's a really common optimization when you solve this problem of harvesting the factors in pairs. Because notice if my target number is 16, when I grab the factor 2, I can also grab the factor 8, which means I don't have to loop through all the numbers looking for factors. I really just need to go up to the square root and then harvest the factors in pairs, and that's exactly what this code does, is grab the factor and then grabs the symmetrical one using division to find the symmetrical factor. And that's way more efficient, just going up to the square root than looping through all the numbers, or up to half the numbers, for example. This is the code that I was talking about that does the caching. This sums up all my code, calculates factors, and then iterates over them and sums them all up, and puts it in sum. This is my the caching property accessor for my code. This looks to see if sum is 0, call sum, otherwise just returns it. So if I've already got one of these guys, if I've already calculated the sum, it just returns it, otherwise it lazily calculates it. And then here's my is perfect, is abundant, and is efficient, which just applies my formula. Get sum minus the number is either equal to, greater than, or less than my target. So that's my lazily apply sum right there. If I've already calculated that sum, I won't have to go through it again. So this is not actually cache, this is just lazily initialized. Got a cache versus the commands. And so if you look at this code, it has three pieces of internal state for 2 reasons. It has partially this internal state to make it more testable. One of the ideas of test-driven development is to break it down in very small methods and pass in dependent data structures so you can mock them or spell them. It makes it easier to test. So that's how some of those internal state end up there. And then the lazy initialization is the other reason we have that internal state, so I can hold on to some and don't have to calculate it as often as possible. This code is very cohesive in that they're very small methods, each single-minded. It follows the composed method style of coding that Kent Beck talks about in small talk best practice patterns. It's very testable. In fact, it was created as an illustration of testability, so it's 100% code coverage. And it is pretty refactorable because it does have lots of very small methods in it. My goal going into this code was I want to solve this problem of number classification, and I want it to be testable as well. But what if I had a secondary goal that said I want both of those things to still be true, but also want to minimize internal state as much as possible and create a slightly more functional version. One of the things we try to do in the functional world is not rely on internal state quite so much. And so this is not using any extensions to Java, still in the Java pre-8 days, but this is a slightly more functional version. And what I've done here is basically collapsed a few of those individual cohesive methods that I had before into one place. So now this is actually doing the determining all the factors and adding them up. This was several methods before, but I'm doing this so I can encapsulate the creation of factors entirely within this guy. So factors now creates this guy and returns the result from it. My sum does the same thing. It sums up all these values when I take in the set of factors. And these guys still work, but notice that I'm calculating the factors every single time and I'm calculating the sum every single time. It was just really inefficient for multiple classifications, but I don't have any internal state where I can hold on to those intermediate results anymore, so I just have to calculate them every time. We will actually see in a bit, we can get rid of this inefficiency using functional programming, using a technique called memoization, but for now we've kind of lost a little bit of the efficiency we have. But if you look at the shape of this code, there's now no internal state whatsoever. And so there's less need for scoping. You'll notice that all these guys are static public rather than private. There's no reason for me to make these methods private because I'm not hiding anything. You make things private because you're hiding the details of internal data structures, but I have no internal data structures. Everything here is completely above board, and in fact, finding the factors of a number is potentially useful outside this number classification business. If I were looking for prime numbers, for example, I would need this code as well. And by making this static public, I can now do number classifier dot factors of some number, and I get that list back without having to tie it up in this whole number classification universe. It becomes reusable at the function level rather than the class level, which is something that we tend not to think about in the object-oriented world because we're so accustomed to class-level reuse. And I'll address that again in just a second. This code is still testable. In fact, this was still done TDD like the code before was. It is still refactorable. I have lost my lazy initialization. Like I said, I'll get that back in a little while, but for now, this is less efficient code. But I think this supports my contention that functional is more a way of thinking that a particular tool set, even in a language that doesn't necessarily have support, like higher order functions, which I'll talk about in a second, you can still write code that's shaped in a more functional style. Now, one of the things that you discover as you start delving into functional programming is it is a both deep and wide ocean of interesting stuff, and there's all sorts of little fascinating tributaries all over the place. What I want to do is pull out a few of those concepts that have some relevance in our world as developers, and I want to talk about and show you examples of all four of these things. First, I'll talk about first class or higher order functions, also known as lambda blocks. These are functions that can be passed as parameters and act as first class data constructs, data structures within a language. Pure functions, which are functions that have no external reference outside themselves. They only rely on the parameters that have been sent into them, and they don't rely on any state outside themselves and don't create any resources outside themselves, like allocate memory or anything like that. Recursion is an alternative to looping that we don't use much because a lot of our platforms are not optimized for it, but there's some interesting cases that for recursion that illustrates Michael Feather's point from earlier that I'll show you in just a bit. And then finally, strict evaluation is this concept about how parameters are evaluated and how eagerly things are evaluated in your language. And this leads us to some really interesting concepts around laziness and lazy data structures that I'll talk about in just a second. So let's talk about each of these things in turn. The first thing I'll talk about are higher order functions. This is what mathematicians tend to call these things. These are functions that can either take other functions as arguments or return them as results, making functions first-class citizens out in your world. And we've had a need for this for a really long time. This is some really common code. This is in Java. This is actually a target of a refactoring exercise, but we eventually get this code down to the point where there's some setup, there's some work, you complete it if everything goes okay, you roll back if something goes wrong, and you finally clean stuff up. And the observation you make once you reach this kind of target in the refactoring world is, hey, this is potentially kind of reusable code. If I replace these two really specific lines with something generic, then I have kind of a template here for doing persistent data access. And so the traditional advice here is to use something like the command design pattern to make this generic. And so that's exactly what you do. You create this, take a command up here, you execute that command as part of your step here, and then in Java, pre-lambdas, you had to do this anonymous inner class business where you create a new command, anonymous inner class instance that has the execute method in it, and there's the actual pieces of work that you wanted to do. Of course, this is all just kind of syntactically clumsy, and we'd like to get rid of this, because really all we want to do there is pass behavior around. And if you look at modern versions of Java, like Java 8 or Groovy, this is actually Groovy, the scripting kind of version of Java. Anything in Groovy inside curly braces is automatically a code block. And so you pass this command exactly the same style that we did before, but now you don't have all the syntactic stuff around it. In fact, what this shows is that a lot of the traditional design patterns, particularly the command design pattern, become completely deprecated when you have higher order functions in your language. If you have lambda blocks, there's no real reason to use this design pattern anymore. In fact, this design pattern explicitly came into being as a band-aid for languages that didn't have a way to pass portable code around as a code block or a lambda block somewhere. And so we can definitely do much better than this. And so actually a lot of these classic gang of four design patterns disappear, command, strategy, and a bunch of the others when you start getting these functional constructs in language. But in Groovy, this is not just a code block, it is also a closure block. And closures have some very specific kinds of behaviors, so I want to spend just a minute and talk about what's so special and magical about closures. I made this example in Groovy, which obviously supports closures. And in fact, all major languages now support closures. So let me show you this example. I have a function here called makeCounter that defines within it a very local variable, set to equal to 0, and then it returns a code block. Now, I don't even care what the code block does for a minute. Just realize that in Groovy, everything in curly braces is a code block, so the return of this guy is a code block. So when I say C1 is equal to makeCounter, C1 now points to one of those code blocks. And when I do this in Groovy, that executes the code block. So what it's going to do is say very local variable is equal to very local variable plus 1. And then because that's the last line in the code block, that'll be the return value of the code block. So if I evaluated the return here, it would be 1, and then 2, and then 3. Then I come down here and say C2 is equal to makeCounter. What that's doing internally is giving me a brand new instance to one of those code blocks. And each one of those instances has their own copy of very local variable. So that when I come down here and say print out C1's value and C2's value, what I get is that C1 has a 4 and C2 now has a 1. What that shows is that both C1 and C2 have their own copy of very local variable. And this is why a closure is different than just regular parameter passing in a language that has parameters. Because it's called a closure because when you create this instance of a code block, when you fire the constructor on this closure, it looks to see what things it's referencing that are in scope. And in this case, this guy is in scope. And so it creates an enclosed environment around this guy, creating a local instance of very local variable that is carried around with that code block and eventually gets garbage collected when that code block gets garbage collected. So this code block is now responsible for holding on to the value of this very local variable guy. Now it's a little bit smelly from a code standpoint to mutate an internal local variable like this and get a result, which is kind of weird. But you can't do this at all in a language without closures. You would have to manage that value yourself. But here, each instance of that closure is managing that very local variable and anything else that's in scope for you. This is a great example of Michael Feather's quote of hiding moving parts. The state of this guy is a moving part, and closures just hide that from you by encapsulating whatever those values are when that code block is created and now get carried with that closure block everywhere it's accessed. This is a good example of letting the language manage that state rather than you having to manage it. In fact, this is a general trend. Over time, you hand more and more busy work to our languages and runtimes, like memory allocation and garbage collection. I've done work in non-garbage collected languages a bunch. Been there, done that, got the t-shirt, don't want to go back. Well, I realized at some point in my career, life is just too short for Malloc. I just don't want to chase those kind of problems. I would much rather think about more significant problems than all this plumbing junk that you just have to deal with to make computers work. And now I don't have to worry about that much because now virtually every language I use is garbage collected and I don't have to think about memory addresses and those mundane details. I can think at a higher level of abstraction. I'll show you some examples in just a bit for this language closure where it actually does for concurrency what Java did for garbage collection, meaning you can write high performance concurrent applications in closure and never once write a synchronized block, and never worry about deadlocks because the language manages all those details for you. This is a trend that over time we see more and more of this busy work of our runtimes because we can. even some things like tests. There's some really great specification-based testing frameworks where you state a bunch of facts about things and then tries to figure out how to break your code. This reminds me, back when I was in university in the early 80s, we used this thing called Pecan Pascal. Anybody here ever heard of Pecan Pascal? This was this piece of software that would let you write one Pascal program and run it on an IBM PC and an Apple II without having to recompile it. They were using this technology that they call bytecode. So when you compiled your Pascal program, it compiled to this bytecode stuff. And then each one of those computers had a virtual machine that ran your code, and it was slower than Christmas to try to run anything on Pecan Pascal, because in 1984, we just didn't have enough overhead to allow you to do something like bytecode and virtualization. It was just miserable. But 10 years later, Java comes along, and we have just enough overhead to allow us to do that. That's exactly what's happening to all these functional programming constructs like map and reduce and filter. We now have enough excess overhead in our runtimes where you can easily do that without taking a big performance hit. And so every language has added those features because we have plenty of overhead now to make those things really, really efficient. First-class functions are basically what computer scientists call higher order functions. They are conceptually the same things. These are functions that can appear anywhere any other language construct can appear. And these are typically closures. But one of the nice things about closures is they allow you to think at a higher level of abstraction. Let me give you a couple of examples of this. So let's say that you have some sort of company process where you're handed a list of names, and what you're supposed to do is go through and eliminate all the single character names, because those are just junk data, capitalize all the names that are left, and return them in a comma delimited list. Now, one way to solve that problem would be to loop through all the names and just get rid of the single character ones, and then loop through all of them and just capitalize them, and then loop through all of them to generate that list. But you never do that, because it'd be screamingly inefficient to go through the list 3 times just to do one step each. And so what you do is do all 3 things in one imperative loop. This is very typical in a land like an imperative object-oriented land, so that's exactly what I'm doing. But when you get lambda blocks, and so this is an example from Java 8 in the lambda world, you can now start thinking at a higher level of abstraction, because you can now say that list of strings name.stream, and now you can apply modifiers onto that string. You can say filter to give me the ones where the length is greater than 1, and then map those to capitalize them, and then collect them all together with a comma as the joining element between them. Now I can think about my problem in much the way I stated it, because this is now more or less pseudocode in the way I stated the problem, and I'm not mired in the details of this imperative loop where I'm having to keep track of indexes and do right things with indexes and all those things. Now I can just think about the problem I'm trying to solve. And so let's say that you wrote that imperative version, and your boss comes along and says, hey, you know, that string processing thing is great, but we need to run it over multiple processors now, because it's really getting slammed. Now you're going to have to go into that data structure and figure out which things to synchronize and which things to block on and all that stuff. But in this land, you can just say, give me a parallel stream instead of a stream, and now it's automatically parallelized. This is thinking at a higher level of abstraction, because you have higher order functions that you can pass in behaviors to these mechanisms. This is an example of what I call thinking about results, not about steps. We get too mired down into the nitty-gritty details of solving problems, and we'd like to think at a higher level of abstraction. Part of this has to do with the way that object-oriented languages tend to work. Because in object-oriented languages, the way that you solve problems is with graphs of classes. So if you look at the canonical example of design in this space, the design patterns book, Elements of Reusable Object-Oriented Software, every single example in that book has a class diagram. Because that's the way you solve problems in a class-based system, is a communicating network of classes. And so you're highly encouraged in this world to create encapsulated data structures and build operations that work on those data structures. That's not really the way they try to achieve reuse in the functional programming world. They try to achieve reuse at a much smaller level. And instead, they build these hyper-optimized machineries around specific kinds of data structures. And so in the functional programming world, you try to get things into the shape of a data structure you already have rather than build a brand new data structure. For example, in the Java world, there are dozens of XML processing frameworks, and every single one of them, the internal details are different. In the Clojure world, which also runs in the JVM ecosystem, which is a list and a functional language, the first thing Clojure does is map that XML document into this well-known zipper data structure in the Clojure world, and then there are all these machinery within Clojure to work on zipper data structures, to traverse them and pull them apart, do XPath-like queries in them. So instead of building a brand new data structure, you build hyper-optimized machinery around the feed. And the idea is you take this machinery plus data, customized with Lambda blocks, pass it into the machinery, and the customization plugs into the machinery and does some specific stuff, and what you get out the other end is transform code. So let me show you a few examples of this. This is a framework called Functional Java that allows you to do functional programming like stuff in Java before Java 8 came out, and it shows a bunch of these functional concepts by leveraging the generic syntax and interfaces in the Java world. And so here's our number classifier, but written in functional Java. So let's look at the differences. And here's the first big difference. Here is our sum, which takes in a list of factors. This is a functional Java list, not a standard Java list. And it says return factors.fold left, add comma 0. Now, how does that sum anything up? Well, that add is actually an enumeration from here. That's a built-in thing from functional Java. But it's still not clear how this works. Here's how it works. So a fold in functional programming is a way of manipulating a list. So you have a list like this. What fold says, what fold left says is, what I want to do is take this list and generate a single value. So what I want to do is take the second element and fold it in on the first element. And the way that I'm going to perform that fold is use this operation called add. So I'm going to add these two together and combine them to make a new first element by adding them, and I'm going to do that again. And I'm going to keep doing that. That's this fold left operation, and when you're done, you're left with a single value that is the sum of all the numbers in that list. So that's a fold operation in functional programming. This is a fold left. Now, of course, with add, it doesn't matter which direction you do the folding, but there's some operators where the order matters. So there's also a fold right that folds in the other direction. There are some other characteristics about so-called recursion and other stuff that play into that. This is a predefined function that takes in two values and returns a single result. That's the thing that you have to have for a fold to work, is some sort of mechanism that takes two values and returns a single value from them by doing some sort of combination. And that's exactly what this guy does. It returns a single result and takes in two integers. If you look at a language where this is built in and not something that is added as part of a library like functional Java, Clojure, for example, which I'll show you an example of a little bit later, Clojure is a Lisp that runs in the JVM, and everything in the Lisp is kind of inside out. So this defines a function called sumFactors, which takes in a list of numbers as its parameter. Factors of number reduces that list of numbers. And reduce, which is another variation of fold left, what reduce says is, give me a collection like this, and a method or function that takes in two values and returns a single result. Plus qualifies, because it takes in two values and returns a single result. And so that produces the exact same results in the Clojure ecosystem for this fold operation in the pre-Java 8 world. So rather than iterating through this, what I'm doing is doing this fold operation, another good example of thinking about results rather than thinking about the steps to get to those results. But there was another instance within my imperative number classifier where I had an iterative for loop, and that was trying to determine factors of a number. So how are we going to do that without iterating all those possible values? So let's say that our target number is 12. How am I going to get the factors of 12 without iteration? Well, the first thing you can do is observe that it's some of, but probably not all of these. These are all the possible values. And it is in fact a subset of those values. So what that suggests is a filtering operation, which is exactly what I'm going to do. Factors of a number is the range from 1 to number plus 1, because ranges in functional Java are non-inclusive, so that gets me off the entire range of numbers. Dot filter. Now, in the Java 8 world, I could just pass a code block here, but this is pre-Java 8, so you have to do this anonymous inner class business. But all this does is create a new anonymous inner class with an F method, single F method, that takes in an integer and returns a Boolean. There's my integer, and it calls my is factor to determine is this true or false. And so, well, the return of this is going to be just the numbers in red here, because it's going to return me the filtered range of those numbers. Now, notice, however, this is way less efficient than the hand-tuned original version I showed you, because remember I had that square root optimization trick? My square root trick is nowhere in here. This is touching every single number in its way to achieve the factors of 12, and so this is temporarily less efficient than that code, but it's at a higher level of abstraction because I'm not having to get into the details of the iteration. I'll let you get that efficiency back using filter in just a second, but for now this is less efficient. So that's the functional Java version of my number classifier. I'll show you a couple of other versions of it here in just a bit as well. Good example, another example, thinking about results but not about steps, which is usually a good thing. And the analogy that I typically give here, I do not for a moment want to suggest that relational databases are functional in nature. They're actually this weird mix of paradigms around language and that kind of stuff, but there's one characteristic that's very similar to functional programming in that when you send a SQL query over, you don't tell it how to allocate memory, you don't tell it where to go to find those data structures, you don't even know where those data structures live. It knows, you just hand it your request and you get some results back. And most of the time that works great. Every once in a while it does something dumb and you want to get in there and tweak it with some query optimization planning or some more details. And the exact same thing is true here, because this is a lot less efficient than the code that we wrote by hand. So what about the times that we want to think about steps and not just think about results? Things that you want to control, like performance. You can get the same kind of results, it's just in a slightly different way using new kind of tools and techniques. So if you remember in my imperative number classifier, one of the cool things here was that I only went up to the square root so that I didn't have to do as much work. I want to get the same kind of optimization back in the functional Java world, and I can do that like this. And this shows the third major category of catamorphism. So here's my factors of optimize. What I start with is by going from factors to 1 up to the square root of the number. So what this is going to do is basically harvest all the factors up to the square root using my is factor method that I had before. And it's going to put that in factors. Now, for the return of the function, I'm going to return factors.append. So I'm going to append onto that list. Then, the thing I'm going to append is factors.map. And this is the third of these. We saw reduce, we saw filter. Map now is the third of these. What map does is take a collection and a function, a higher order function, and applies that higher order function to every element in the collection, leaving you with a transformed collection. And so what this is going to apply to each one of those is to return me number div I. And so what this is going to do is generate all the values up above the square root of my number and append it onto the list of numbers that were below the square root of the number. And there's this one last little thing down here, nub. What nub does is remove duplicates. Now, in a perfect world, and in fact, if you're in a language where these data structures are needed, it wouldn't really matter if you used a list or a set here, because the same operations would be there for both of them. But it turns out in functional Java, there's a richer set of APIs on list than on set. And there's an edge case here for whole number square roots, like 16. They end up getting added twice, which means that functional programming has no excuse not to do unit testing. That's how this is discovered, was by unit testing. What nub does is remove duplicates and basically convert the list into a set, which has no duplicates. So that's what a bit of implementation detail here. But this is optimized in the same way that I did my imperative version, but using these building blocks in a slightly different way. Now, if you look at a language that has all these functional constructs in it, you can have a much simpler classifier. This is one written in Groovy, and Groovy actually uses scripting language names for these functional building blocks. So my isFactor is the same. This is find all in Groovy, which is their filtering mechanism. And so ranges in Groovy look like 1 to the number, find all, and that's a code block that I'm passing in. And the thing I'm finding is where isFactor is the number. This has some a little bit of syntactic magic in it from a Groovy standpoint. That's the range. The find all here, you'll notice it says isFactor number and then it. Where did this it guy come from? Well, that's a little bit of an optimization in the Groovy world. You could have written it like this, where you name a parameter and then use that parameter. This is such a common idiom that there's syntactic sugar in Groovy that says, well, rather than do a single parameter and then reference a single parameter, you can just use the built-in it to reference a single parameter, so you don't have to actually put it in there and pass it around. So that's where that it guy comes from in that code. Some of factors here takes the factors of number dot inject. This is its version of reduce or fold. 0 is the seed value, so that's what you start out with. And notice this is a code block that takes in 2 values and returns a single result. And that's exactly what I want for a reduce or inject. Is something that takes in 2 values and returns a single result. That'll boil that list down to a single value, which is the sum of those factors. And then there's my is perfect, is abundant, and is deficient stuff, which is unchanged from the previous one. Okay, so here's a little bit of an academia alert. This happens sometimes in the functional programming world. You'll bump into some places where the mathematicians have actually had some say in this world. And here's a good example of this. There's this really useful technique in the functional programming world called currying. This was named after a mathematician, 20th century mathematician named Haskell Curry, who was so influential that his first name became the name of functional programming language Haskell, and his last name became the name of this mathematical technique that's also quite common in computer science called currying. And his observation was, from a mathematical standpoint, that was given some function that has multiple parameters, you can mathematically transform that into a chain of single argument functions that just get called serially from one another. So it turns out that works in mathematics. It also works in computer science. You can take a multiple parameter thing and convert it into a chain of single function calls. That's currying. There's a related concept in computer science called partial application. Partial application fixes the number of arguments to a function, producing another function of a smaller arity. Arity is the number of parameters that a function takes. And so the idea of partial application is, let's say I have a function that takes in 5 parameters. What partial application does is say, give me fixed values for 2 of those and return a function that takes 3 parameters. That's partial application, not currying, because to get it to currying, you have to get it all the way down to single parameter functions chained together. So in currying, you never have multiple parameter functions. So this is like a slightly less strong spice than currying. So this is like maybe salt. But this is how it works. This is in Groovy, which supports currying. I can say product is equal to a code block that takes in an x and y and returns the sum of those 2 guys. I can now come along and say, well, I want a version of product that always multiplies by 4. And so I can say quadrate is equal to product.curry4. And what that does is fix the first value at 4 and just gives me a function now that takes a single parameter that will always multiply by 4. This is basically just syntactic shorthand for creating a quadrate function that takes a single parameter and always multiplies it by 4. That's what currying does for you. So here's an example of taking product. I can create from that a quadrate, an octate, and have one that multiplies by 4 and one that multiplies by 8. And you can call it either way. These are just syntactic differences in that group. Now, it may seem like these are very similar concepts, and they are, and Groovy has actually exacerbated this by supporting partial application but using the currying, that same function. So let me show you an example here. So let's say you have something that calculates volume with height, width, and length. You can create an area version function by currying the first dimension so that you now have something that takes in 2 parameters and returns their area. Now, if I wanted to create a length by partial application, what I would do is curry the first 2 of these. That's partial application. If I wanted to do this via currying, I would curry them one at a time. The end result is there's no real difference from an implementation standpoint. The difference here is that the groupie guys are playing kind of fast and loose with their nomenclature, because this should never exist, this ability to do that. That's really partial application, but they're calling it currying. This is why mathematicians and computer scientists can never get along when they bump into each other, because this drives mathematicians crazy. But notice this is a really useful concept, because basically what you've done here is created function factors. So a really common use for this, let's say, notice that in the traditional kind of web framework world, one of the things that you do is through inheritance or composition or something like that, you inherit something like database connectivity. So you don't have to deal with that. It comes from sort of database connection pool or something like that. In the functional programming world, what they would do, rather than encapsulate that as something that you inherit and carry around or pass it as a parameter, what they'll do is have a function that every database function takes in database connectivity parameters, and once you've decided what those are, you go ahead and fix those by currying and return a function that only takes in SQL query and parameters. That database connection parameter has been fixed by the framework, but you don't have to worry about it as a developer. In fact, you never see that even as a parameter because it's been curried away, and you're now dealing with a function that just takes in SQL and parameters, even though that implicit curried database connection then is there. This is a way to achieve function reuse as well. So if I have an adder, I can create an incrementer based on that just by currying the first parameter. You can also composite these things together. So here's the compositor that basically says, given 2 functions and a parameter, return me the composite of calling one function inside the other. And now I can do something like a 32er composites quadrate and octate together. So I now have something that multiplies things by 32, because it multiplies by 4 and then by 8. This is really just tricks on the closure class in the Ruby world. Currying is a first-class citizen in languages like Scala. Scala is a really strongly functional programming language, and in fact, this is one of the examples from the Scala documentation that shows how currying works with filtering. So here's their divides by, and you'll notice the 2 parameters are split out separately like this, allowing me to curry one of them if I want to. And in fact, what this guy is expecting, this filter guy is expecting a list of integers and then a predicate that takes in a single integer parameter and returns a Boolean. My divides by takes in 2 parameters here, but you'll notice when I call it, I say print line filter numbers and divides by 2. What I'm doing is supplying the first parameter, and now I'm left over with a function that accepts a single parameter, which is what this guy's expecting, which will fit into this filter routine. And so this is another way, now I can do divides by 2, divides by 3, and it plugs into this machinery that's already there through that curry function. So this is a very natural syntax in a functional language like Scala. Next, let's talk about pure functions. These are ones that have no memory or I/O side effects outside themselves. In fact, we saw some examples of pure functions in the slightly more functional Java version that I showed you. Up until now, though, this idea of functional purity was more useful to runtime designers than developers, mostly, because your runtime, if you have a pure function, can do some really wonderful things with it. For example, if the result isn't used, your runtime can just strip that function out because it's never going to be called if nobody uses the result. You can also, if you have a bunch of pure functions, run them in parallel because they're not impacting the outside world because there are no side effects outside themselves. And the runtime can also do things like change the execution order of pure functions and be smart about that. You can also make this observation about a pure function. That when you call a pure function with a particular set of parameters, it yields a constant value. So the math.tangent function that's built into your language is a good example of a pure function. When you call math.tangent today, you don't worry that when you call it tomorrow, you're going to get a different result with the same value as today because it's a pure function. It relies only on its parameters. So you could, for example, if you were doing tangents for a lot of different values, build a table of all these tangents, because once you determine the tangent for 55, it's never going to change because it relies only on its parameters. But this is a really nice thing for us now because of this technique called memoization. Let me give you an example of where this is applicable. So this is my Groovy version of my classifier that I showed you before. Let's say that I have this scenario where I keep calling this over and over with the same numbers, and it's kind of expensive to do this summing every time. So I want to create a version of this guy that caches sum, so that every time I see the sum for the first time, I cache it, so that if that number comes up again, I already have that sum in cache. So that's easy enough to do. I'll create a version of my with a sum cache, initialize that guy to an empty hash table, and now if my sum cache has that number in it, I can return it. Otherwise, I calculate it, put it in my cache, and then return it. You've probably all written some handwritten caching code like this at some point in the past. You never have to write this code again because of memoization. As long as this is a pure function, as long as the thing that determines sum is a pure function, which it is in this case, then I can memoize it. So sum factors is a code block that takes in a number and does this inject business. Now I can say sum of factors is equal to sum factors dot memoize. And I'm all done. Now the runtime will cache those parameter values for me, and every time it sees a new one, it will return the cache value. I never have to hand write that cache again. If you're in a language that has memoization, you never have to write any kind of function caching again, because the language will handle that for you. And in fact, in Groovy, you can customize the way this mechanism works a little bit. There's a memoize at least this many elements, memoize at most this number of elements. A good example of some new different tools at your disposal. Now, one of the things that I'll show you a reference here toward the end of a book that I'm working on right now called Functional Thinking, which is these ideas. And when writing up these examples of memoization, I tried as hard as I could to write a hand-tuned cache that was faster than the memoization stuff that's built into Groovy, and I didn't get anywhere close, because you know what? They cheat. They have access to stuff that I don't have access to, internal data structures and other stuff. Frankly, they have access to stuff that's probably not safe to give me access to. And I'm okay with that. As long as they write highly optimized memoization code, I never have to write that code again in my life. That's another moving part that has disappeared for me having to deal with. Remember back when I was showing you my slightly more functional version in Java, and I was lamenting the fact that we had to do all this extra work down here? But this guy is a pure function. So in the Java 8 world, which supports memoization, you could have the slightly more functional version and still have as much efficiency here, because you can memoize both factors and sum and only ever have to calculate those for a certain number one time ever. So now this becomes a trade-off of how much memory do you want to use for your cache versus how efficient you want to be without doing those things. Great example of eliminating moving parts. Those internal state variables that I used to have can now go away because the runtime is managing those things for me. The next thing I want to talk about is strict evaluation. And this is the second place in that talk that we end up in this kind of academia alert. This is pseudocode. What do you think this is going to return? I'll give you a hint. You may run into some problems around that element that is in this. But it turns out this is one of those it depends answers. It depends on if your language does strict evaluation or non-strict evaluation. Because in strict evaluation, all elements are pre-evaluated, but in non-strict evaluation, elements are evaluated as they're needed. So in a strict evaluation world, when you try to execute this code, you're going to get div by 0. Because it's going to try to evaluate that before it tries to execute that function. In a non-strict evaluation world, you're going to get a 4. Because the attitude here is, you didn't ask me how many are there and oh, tell me if one of them is poison or not. You just said how many are there. Now it turns out you'll die if you turn to the third one, but hey, you didn't ask me that. You just asked me how long it is, and I told you how long it is. This is laziness. And some languages have this built in as a concept. It turns out Laziness and immutability are really closely related to one another because it's very easy, it's much easier to make immutable things lazy than it is mutable things. So let's talk about laziness for just a bit. Now, most of the time when you hear about laziness, has a negative connotation, kind of like this. This is my favorite exemplar of laziness, because you can just see the thought process of written into this profound bit of laziness. You know, it's hot out, and I really want to barbecue, but the cord won't quite reach long enough. It's worth observing here that if you look very closely, this is a round European style plug, so this is in fact 220 volts of electricity, not the usually 120 volts we have in the US. So that's going to be pretty shocking when that happens. This is not the kind of laziness we want. We actually want beneficial laziness like this. You can actually achieve laziness even on top of something like Java without lambda blocks. There's a framework out there called Totally Lazy that is heavily inspired by this thing that comes from Google Code called the Hamcrest matchers. Hamcrest is this fluid interface for writing matchers for a JUnit test. But Totally Lazy has taken advantage of these guys. So for example, my is factor in Totally Lazy, it says return where remainder of n is 0. So those are all Hamcrest matchers pulled in from, through static imports. But you can see this actually reads, it's a little bit verbose, but it reads pretty nicely. Range from an end-to-end filter based on is factor of n, and it has memoization built in, so it calls it memorize, but that's memoization. And then my sum factors, there's a reduce function, it has in here. And then for my is perfect, I can do equal to, greater than, or less than. So there's the example. My is factor guy uses those Hamcrest matchers to make those more fluent. It factors returns that range. And then there's my memorize, which does memoization for me. So you can do memoization even if you don't even have higher order functions. This is a good example of that. This works on Java, pre-Java 8. But you can also build lazy data structures if you want. So here's an example of building your own lazy data structure. And the trick here is when you're building a lazy data structure is to hold on to the head, but the tail is just the way to generate the next value. So rather than hold on to a value in the tail, you hold on to a code block that will generate the next value. And so that's exactly what I have here is a head and a tail. Head is a value, and a tail is a code block that will generate the next value for you. When you have a lazy data structure, you have to tell it how many elements you want. So this is how I get from the head. And I'm actually doing this internally, imperatively, but this acts lazily from the outside. Because I say, give me this many elements from the head. And so I go through here and iterate n times and generate those values from the tail. And then return the values from the head. And I can also, with this lazy list, filter the results. And this is recursive filtering. So I take in a closure block that is my predicate that determines should this element be on the list or not. And if the predicate of head is true, then I want it on the list. So I want to prepend the head onto the list, the rest of the list. Otherwise, I want to just return the tail because the head doesn't get to be on there. It doesn't even miss my filter criteria. So that gives me a lazy list. I can now use this to do things like create a lazy list of integers. So this prepend guy basically takes in a value in a closure block and builds me a new lazy list from it. If you're used to a language like a Lisp background, this is just a pseudonym for the cons method or function in Lisp, which constructs a new list. So I can use this to say the integers around n prepends n and then a code block that generates integers of n plus 1. And so I can come down here and say the natural number starting from 1. And I can now say natural numbers get head 10, and that'll give me the first 10 natural numbers. I can also say even numbers or natural numbers dot filter based on even numbers, and say get 10, and it will give me 10 values, but it'll be this lazy list of 2, 4, 6, 8, etc. Now this is one of those things that you run into as you start playing around with functional programming languages. Is there's a lot of differences in nomenclature. A lot of these ideas were kind of developed independently and were only realized after the fact that they were part of the same kind of concepts. And if you want a place that you can really do a deep dive into some really fascinating stuff, look at the category theory stuff around functional programming. Category theory is this mathematical field that came about in the 80s and 90s where they started looking at physics and computer science and biology, and they started realizing there are all these commonalities across all those fields that didn't look common at all, and gathered all that stuff into category theory. And there's a lot of computer science stuff that ends up in category theory as well. But the side effect of this is that you find a lot of different terminology out in the world. So for example, what functional Java calls a fold left, Groovy calls an inject, and another language is going to call reduce. Now there are slight differences between a fold and a reduce, but those differences are not consistent across languages either, so those are frequently synonymous with one another. This, in the functional Java world, and most of the world calls this filter, whereas Groovy calls this find all, so you find these differences in a bunch of different places. Back to my lazy collections. This is the tersest possible finds me only perfect numbers finder that you could have. This is basically not just two functions, give me all the factors and then tell me if it's perfect or not from those factors. I also have a next perfect number from, which imperatively goes and figures out what the next perfect number is. This is going to take a really, really long time, by the way. I think they've identified something like 16 perfect numbers ever. And the 16th perfect number is like 5 times the number of molecules in the universe or something crazy like that. So this is probably going to take a while to run if you try to get the 16th or 17th perfect number. So buyer beware there. But this is actually the perfect case where you might want to do a lazy list of perfect numbers because it never generates a value until you need it. And that's one of the benefits of laziness, is that it doesn't do extra work that you don't need. And so using my prepend guy here, I can say, give me the perfect numbers of n, prepend n, and then the perfect numbers starting from n as the next perfect number. And I can come down here and say, give me the perfect number starting from 1, and I get back, when I say get to 3, it gives me the first 3 perfect numbers in a lazy list. Laziness is really interesting because it means you end up doing a lot less work from a computational standpoint. But it's also heavily related to immutability, as I said before. So the language that is most notoriously lazy, where everything is lazy, is Haskell, because everything is immutable. Clojure is also, does most of its data structures are lazy. In fact, there's a core data structure in Clojure called a sequence that all the other collections are based on, and sequences are lazy. And so almost every list operation you do in Clojure is also lazy, but it's because everything is immutable by default in Clojure. So laziness and immutability very often go together. In languages that don't enforce immutability, it's harder to build efficient lazy data structures. And you see those as the default in languages that really like immutability. Okay, the last big topic I want to talk about is concurrency. And this is one of those places where the differences between the functional programming languages and the imperative languages are pretty stark. And this is a good place to start talking about the real difference between the two main functional languages in the JVM space, which are Clojure and Scala. So let's talk about Clojure first, because it is the most radical departure by far of any of the other languages that run on the JVM. There's a terrific keynote by Rich Hickey, the guy who created Clojure, called Simple Made Easy, that's available from the Strangeloop conference. Highly recommended. This is from 2 years ago, but it explains a lot of the design philosophy in Clojure, and it's pretty fascinating stuff. As I was looking for this picture of Rich, I also bumped into this one, which is very Rich Hickey. This says, state you're doing it wrong, which is a very Rich Hickey thing to say, because Clojure, everything in Clojure is immutable except for one kind of thing, which is a reference. So everything, all data structures in Clojure are immutable. And basically what he did as he was putting Clojure together is he figured out what makes concurrency so difficult and so error-prone in Java, and a lot of languages that were heavily inspired by Java. It turns out that it's this concept of variables. Because variables were designed before they ever thought about concurrency. And so they made a lot of really flawed assumptions when they created the concept of variables, because they assume one thread of control in one timeline. They're not atomic unless you wrap them in synchronized blocks, and they manage all these deadlock detection and all that stuff yourself. So they're not very composable. They have subdivisibility rules, and when you get to concurrency, because all that was layered on after all these assumptions were made, then you're pretty much in the lock and pray world. It's very difficult to get concurrency right, and in any of these imperative object-oriented languages because concurrency was always layered on much after the fact of all the other core structures in the language. The problem that Rich identified in Java is that you have one mechanism, a variable, that has multiple jobs. And it's usually a bad idea in a programming language when you have one thing that's doing multiple jobs, because it's probably doing some of those jobs really poorly. And that's exactly the case here, because variables in Java are responsible for the state of the thing and its value and its identity. So all three of those things are kind of conflated together into variables. And so what Rich did in Clojure is say, okay, I'm going to fix this problem, make concurrency easy in Clojure, by saying everything in Clojure is immutable. You can't change anything except one thing, which is a reference to something. And Clojure completely controls when you update a reference, so they can control concurrency. So what Clojure did was split out this idea of a variable into identity and value. The identity never changes, but the value can change over time, and the combination of the identity and a value at a point in time is its state. So Clojure is one of the first languages that thinks about time as a first-class citizen. Because most object-oriented languages treat everything as a snapshot instant in history, that the whole universe looks consistent for the snapshot after snapshot, but it doesn't think about the state changes that happen along that way. And so what Clojure does is control this. It controls this update semantic, and by controlling that update semantic, it handles all threading problems. There's this thing called the epical time model in Clojure, where you have references. So this dotted line is a reference over time. So it's a single reference to something, and it's pointing to a particular value at a point in time. You apply a pure function to it to update it to a new value at a new point in time. At some point, some observer is going to look at that value and dereference it, or it may just look at the reference itself to carry it around somewhere without dereferencing it. That is its snapshot in time, that is its state at a particular point in time when somebody wants to reconcile what value does its identity point to, and these guys are always just pure functions. Because Clojure manages all this mutation for you in these references, it can guarantee consistent state always. And so they have built on top of Clojure this thing called software transactional memory. Clojure has a full-blown commercial-grade software transactional memory mechanism inside it, which gives you ACI but not D. So it gives you atomicity, it gives you consistency, and it gives you isolation. It doesn't give you durability because it's all in memory. It's software transactional memory, not software transactional database. But it has the same kind of characteristics, so you can say, for example, in the Clojure world, that I want these two references to update themselves within a transaction, and it'll guarantee that both of those values get changed or neither of them get changed. So you have transactions just like you have in a relational database. It's really intelligent about retrying transactions in case one fails, and it's also smart about doing this technique called barging. So if you have a transaction that's been trying to get success for a while and it can't, it'll bump the priority on that transaction up to try to get it to achieve success because it's fighting with some other transactions. So there's a fair amount of sophistication built into the language around how it does all this transaction stuff for you. You never have to interact with this if you don't want to. In fact, the syntax for it is really super simple. So this is the syntax in Clojure. This is how you create a reference to something. So this is a messages, and this is a reference that points to no value, so it has an initial value of nothing. I can dereference one of these references if I want by calling the deref function on it, like that guy. But this is such a common thing in Clojure, the syntactic sugar. If you just put an at in front of something, it dereferences it automatically. So if I look at that guy, it has nothing in it. When I want to alter some reference that I have, I call an alter, passing in that data structure and then the update function of whatever arguments that it takes. That update function is going to be a pure function. And what that's going to do is take it from a single transactional step from the old value to the new value within STM. And this is what that syntax looks like. I've got to add a new message to my collection. What this says is alter messages and can join this new message onto the end of it. But you also notice this do sync thing here. If that's not there, this won't work. I will get a runtime exception saying you're trying to mutate something outside a transaction, and I won't permit that. So that is the transaction mechanism. But I can have as many lines of code as I want in here, and it'll do them all within that same transaction. And you never have to worry about this. Clojure will guarantee no deadlocks ever, no synchronized blocks by hand. In fact, there's no syntax in Clojure to even create a synchronized block, because it makes no sense in here, because it manages all this concurrency stuff for you. The nice thing about this is, now in Clojure, when you use filter, map, or reduce, it automatically uses all the processes on your machine and automatically makes it multi-threaded. You don't have to do anything. It just happens because of the built and the way the mechanisms inside the language are built. You now automatically get concurrency for any kind of map operation you want, and you can tweak that in a variety of different ways. Clojure, there are really only 2 STM implementations for real out in the world, and it's not surprising there are languages that heavily rely on immutability. So Haskell and Clojure are the 2 that have real STMs out in the world. The COR team tried a few years ago to write an STM implementation and ended up abandoning it because it's just too difficult when you have mutability to manage all the state that's in flux inside software transaction memory, so that immutability turns out is the enabling factor to have something like STM. Really, really sophisticated mechanism, and one of the more sophisticated mechanisms in modern languages to handle things like concurrency. And in fact, this shows that Clojure is built very much as kind of a destination language. They're not really trying to make it super easy for you to transition from whatever you are to Clojure. You can always call back from Clojure into the existing Java ecosystem, but it is a very clear engineering vision. I mean, they chose Lisp, so that's a pretty bold move from right out of the gate, is to choose a Lisp. They have good reasons for doing that, but it is very much a software engineering vision in Clojure. Scala is also kind of a new vision for writing stuff in the JVM, but they are much more derivative of Java. They're building a much easier path from the Java world over toward the more functional world. And so what they've done is more kind of encapsulating the existing things that are there rather than building brand new mechanisms. So Scala doesn't have anything like software transactional memory, but it does have things like actors. So let me show you actors. So in yet another variation on this number classifier guy, or trying to find perfect numbers, notice that if I'm trying to find the factors, if I'm looking for factors for 16, trying to determine if 5 is a factor has nothing to do with trying to determine if 8 is a factor. So I can do those at the same time in parallel if I wanted to. So I want to create a parallel perfect number finder that uses actors to do that. And so what I'm going to do is use an isPerfect method to take some candidate. I'm going to create a range here and a number of partitions based on that range. So this might be number of CPUs you have, or number of cores you have, or something like that. And hold on to myself as the caller. Now for the number of partitions I have, this is the range, the lower and the upper. So if my number is 16 and I have 4 processors, what this is going to do is say, okay, first actor you handle is number 1 through 4. Second, you handle 5 through 8, etc. And then I'm going to create actors. Each of these actors basically acts as a standalone entity, and they can have local variables inside them, so they act as Clojure blocks. And so I can have this partial sum guy in here, and what this is going to do for this particular candidate for lower to upper, this is my is factor business. It's a candidate mod j is equal to 0, then add it to this partial sum. And this is the syntax that says from this actor, send this message back to whoever invoked this actor when I'm done. That's what the exclamation point syntax that was borrowed from Erlang. And so this, after this actor has figured this out, will send its partial sum back to the caller. Now this code looks at the number of partitions, and then while I'm expecting responses, receive is where you receive those messages from all those actors. So this will block waiting for those calls back from actors. Every time I get one, it's going to send me a partial sum, which I'm expecting to be an int. I decrement my number of responses I'm expecting, add it to partial sum. After I've received all of them, I can determine, and this is the last line of the function, so the return value, sum is equal to 2 times the candidate. That means it's perfect, so that's either true or false. So this is a good example of taking the existing building blocks of Java, all the threading primitives that are in Java and wrapping it in this really nice actor kind of API so that you can deal with it without dealing with all the low-level details. A good example, in fact, of eliminating moving parts and thinking about results and some new different tools to apply to problems like this, and a great example of eliminating those moving parts, synchronized blocks, and all those other complexities. So walking away from this, what can you do to make your life more functional starting tomorrow? One thing you can start thinking about doing is immutability over state transition. A lot of modern languages don't have really great support for immutability, which is a shame because this is one of the really great entrees into other useful things. For example, most modern programming languages now, string is immutable. But you also notice that you never have to worry about strings in threads. You never have to worry about protecting updates about strings in threads. You can just pass them around anywhere you want. That's purely because they're immutable. So when you have an immutable data structure, they're inherently thread safe because they're immutable. And so that makes threading much easier everywhere if you have immutable data structures everywhere. But it's a little bit of an uphill battle in most modern languages because they're not optimized for immutability. I think that's something we're going to see more and more embracing of over time. Things that are immutable are much simpler to construct and test. They're automatically thread safe. You don't have to have a copy constructor. No clones needed. They make really good map keys and set elements. And you really shouldn't use mutable data structures as map keys and set elements because now your map will get out of whack. You don't have to do defensive copying. And they also have this feature that Josh Block calls failure atomicity. Most languages that come from this era like Java, there's a guarantee that constructors never throw exceptions. You either get a null back or you get a real object back. And if it's immutable and you get a real object back, it's never going to be in a failure state after that. That's what he calls failure atomicity. Once you actually get non-null back, you know it's going to be in a good state forever because nothing can ever change it if it's immutable. That's nice. But it's really hard, for example, in Java to make things immutable. You have to make the class final, all the fields final, all the states set in the constructor, no mutating methods, and defensive copying any immutable object fields. This to me sounds like a lot of moving parts. And of course, one of my mantras throughout this talk is to let the language handle as much of this kind of stuff as possible. I said earlier, let it manage state, but let it manage other stuff as well. So Groovy, the scripting language version of Java, has added an annotation that you can tag onto something and make it immutable, and it does all that busy work for you by having that immutable annotation. So we don't have that in Java yet, but you can in a language like Groovy, and it does all these magic things for you. You put those as immutable, and there's a good example of hiding some moving parts. Try to focus on results over steps and try to work at a higher order level of abstraction. Anytime you find yourself iterating something, there's probably a better way to do that. A filter or reduce or one of those higher order functions like that. Think about, is there a way I can express this problem closer to the way I'm thinking about this problem rather than translating it into these very low level details. And try to think about composition over structure. We'll talk about that in a second. And declarative over imperative. This is one of those places where domain-specific languages are pretty common out in the world now, and most of these modern functional languages have really good support for domain-specific languages. Languages like Scala and Clojure have really good support for that style of coding. But you'll notice even in the example I showed, that company process example, that code looks much more declarative than imperative because I'm just stating the things I want and then passing in these higher order lambda blocks to customize that machinery that's already there. That's exactly what we're talking about. So to summarize, functional programming are new ways of thinking about old problems. We're gradually ceding more and more control to languages runtime, and that's a good thing. Every major language now has higher order functions or lambda blocks. Java was the last big holdout, but it has them now and officially there. Every language has them. JavaScript has them. Any language you can think of has this mechanism in it, and you can start taking advantage of some of these nice things. There's some immediately beneficial starting steps like embracing more immutability and thinking more at a higher level of abstraction. This is aligned with language trends. Every language is going to have these and continue to optimize them. And new capabilities give you new ways of thinking about problems out in the world. And I'll leave you with a little bit of a kind of a mind-bending example of that. In the closure world, there's this thing called Datomic, which is a commercial database product written by the core closure team. And you can get an open source instance of it to play around with. But the cool thing about Datomic is that it is an immutable database server. So wrap your head around that for a second. So once you put something in it, it never goes away. And so your first thought is, well, that's wildly impractical, so I'll just fill that thing up in a couple of weeks and we'll be all done. But it's a value-based data store rather than a record-based data store. So, and this is an oversimplification, but how many times does the number 2 show up in your relational database right now? What if it only showed up one time and everywhere that needed to reference it pointed to it? Because it can never change, there's no danger of anybody updating it and affecting somebody else because everything's immutable. And so basically what Datomic does is gather your universe of values together and there are references to all of them. And so that's not this huge set of things, because it turns out nobody has this huge set of values. In fact, if you did, you'd blow out your relational database way sooner than you would blow out Datomic, because you'd have those core values repeated all over the place. But it makes a lot of things really simple. So one of the things I'm going to talk about a bunch in the continuous delivery workshop on Thursday that I'm doing is this problem in the traditional kind of continuous delivery world of what do you do with relational databases. So relational databases, there's this technique called migrations where you programmatically build up changes to your relational database. But then sometimes you have to go backwards to get to a previous build, and that's really hard and complex and cumbersome. In Datomic, there's no such thing. Because if you want a previous version of your database, you just walk backwards to that version, because every version that has ever existed is still there, because nothing ever mutates in it. And so the entire history of your entire database, including all the DDL, is always there for you to look at. So I now have a question for you. I notice you're using a relational database. Why are you destroying valuable company data every time you do an update in that relational database? Because you're destroying the old value and putting a new value in its place. Well, it turns out we have to do that because hard drive space is so expensive. We really need to modify our architectures to optimize for, oh, wait a minute. Relational databases were designed where resources, physical resources, were really expensive, and so most of the complexity in dealing with relational databases is record locking and all that other stuff, because you're conflating updates and creation and reads on top of one another based on this premise that is no longer valid. Because resources are dirt cheap now. Amazon will sell you resources for pennies on the dollar now. Resources and hard drive space is not our big problem. The crazy complexity we've created because of those limitations are our big problems right now. And things like Datomic are fundamental rethinking. What if hard drive space were essentially free? How would you build a data storage mechanism? And that's what something like Datomic looks like. So without thinking about the constraints of 20 years ago, what are the constraints today, and let's build something around that. So for more information about this, I'm actually writing a book about this subject. It's going to be published in O'Reilly very soon now. And there's a series of magazine articles on IBM Developer Works that this book is being based on, and that's all the stuff that's out there right now. I have just a couple of minutes left. Does anybody have any questions about this? Yes? When should you use functional programming? Well, I mean, this is just a paradigm. So you can solve, this is any problem that can be solved in object-oriented programming can be solved in functional programming. So but there are some things that are much more amenable to one style versus the other. So I think user interfaces, for example, are really good for imperative code because you have all the shared state and you can modify it. I actually think web applications are perfectly suited for functional programming. Because functional programming is really about transformations, pipelines of transformations. Well, that's all a website is. It's a bunch of transformations, take in this input and produce this result. That's a pipeline. And so things like web applications are perfectly applicable for this. And you know, it's going to be case by case. There's a pretty interesting case study, if you're interested, by one of my colleagues, Ola Bini, for this company called Anai Systems. And they ended up building, they own patents on these microbiology patents. So if you have, what they do is take your genome and the genome of your cancer and do some analysis on it and come up with really, really super targeted treatments for your cancer and your genome. And they wrote all that in Clojure and Neal for J. And Ola, in the press release that they released after that, said that it would have been so complicated, it would not have been practical to build it in any other style. So and it wasn't even Clojure, it was the functional programming stuff and the data manipulation stuff that got them to the point where it was a feasible project. So it would not have even been feasible if they chosen another platform. So it's, there are certain problems that certainly limit us up to one shape or the other. Other questions on this? You just want to get out of this hot room. All right, and I'll set you free from the hot room. Thanks very much for coming.